with Quantinuum. My name is Hiraiwa.
My name is Miori. Thank you very much for coming today. So I'm so happy to having me to this meeting. Thank you very much. And 本日ですね、
So QC were staff people, all the people who supported this conference. I want to thank them all. And for myself, I'm going to talk under the title Quantum Chemistry in Action, a Global Perspective. So I'm with Quantinuum, and I am in charge of enterprise sales at Quantinuum KK. And yesterday, our scientist Yamamoto talked about the details of our technology at Inquanto. So for myself, I'm going to talk what you can actually do by using Inquanto. So talk about the use cases. Today's agenda is here. So I'd like to first briefly introduce our company once again, and then I'll talk about our Inquanto quantum chemistry calculation package, and I'll talk about the use cases. So globally, what kind of collaboration have we done with what kind of companies? That's what we'll explain. So first about Quantinuum. I think I would be happy if you remember from yesterday. So last year, Cambridge Quantinuum, a quantum software developer, and ion trap quantum hardware developer, Honeywell Quantum Solutions, merged to create our company, Quantinuum. So it's a new logo, and we're distributing the sticker with the logo. So please come and we can talk. We're a global company, more than 350 scientists, and we have several scientists in the Tokyo office as well. So we're really a science and research-focused company. And as I said, because of the business merger, we now cover the full stack from hardware to software. We're one of the few companies that covers the whole stack. This shows the overview of our business. Our core technology is Ticket. By using that, we can develop and provide a quantum computer from hardware to software. And we have the H series. We have high performance machine. And the Ticket is hardware neutral software platform. So we can handle ion trap hardware and superconducting machines. So you can connect to various types of hardware. So Ticket is hardware neutral, and also optimization circuit and noise correction technology also included. And so by using that, you can implement the quantum computer on error-prone NISC device. And using this kind of platform, we develop applications, and we handle a wide range of topics, machine learning, cybersecurity, etc. This time, we're focusing on quantum chemistry, and we're going to focus on the Inquanto, which is the product for that field. So using these kinds of applications, with the industry partners with their use cases, what we are conducting joint research and discussion about how quantum computers can be used. So about Inquanto, I believe that you are familiar with us. So we provide, so I'd like to talk about this quantum chemistry calculation package Inquanto. So the quantum computational chemistry, its superiority should become evident in the near future. In the NISC era, how to create quantum advantage? Well, that's tightly connected to the situation of hardware. The reason is, in implementing quantum algorithms, well, of course, increasing qubits is important, but also to have a stable to increase the number of stable qubits is also important. So if you want to have a quantum advantage with NISC, then hardware, you have to have research from both aspects, hardware and software, and to have a fault-tolerant computer in the future. Well, with the current NISC device, how can we demonstrate the quantum advantage? I think that's a quite important topic in research. And in Quanto, so it's Python-based quantum chemistry calculation package. So various types of NISC devices are available, but there are noises. And so we can implement quantum chemistry calculation even on such devices. And as well, the ticket, as I explained, is here, so it's based on the ticket. And so also there's noise correction technology for chemistry calculation. And so using the current NISC device, you can maximize the performance and conduct quantum chemistry calculation. So it's modularized, so it can be customized by the user. And if you subscribe to this in your environment, based on your use cases, you can customize it. So from here, I'd like to talk about the R&D collaborations with Quanto. So globally, what the kind of use cases have we been researching on with what kind of companies? That's what I would like to talk about. First, going back, I think you already know this, but just to recap, computational science. Well, you calculate the electron status and energy, and you predict the physical properties, and you feed back to the design without experiment. By calculation, by computation, you can accelerate the development. So that's what's expected of this tool. And what was unexpected for me, I mean, I'm not a chemical computing expert, so what was unexpected for me was that it's very difficult to calculate the electron state. It's very difficult to do with conventional computers. And so you have approximation calculation. But when you want more precise computation, there are issues. And there's expectation that the quantum computers can be useful there. So to repeat, so in Quanto and quantum computer, where can it be used for chemical calculation? Some technical terms here. The target is Hartree-Fock method, where there is not sufficient precision with Hartree-Fock method, so that would be post-Hartree-Fock method. So Hartree-Fock method is mean field approximation, but if you want the higher accuracy calculation, the post-Hartree-Fock method is used. And as I said, if you want the higher accuracy calculation of electron state, that requires a huge amount of computation resource. So there are limits. And with the conventional computers, so you can use quantum computers potentially. So let's go into a little more detail. So in more concrete terms, where can it be used? So this, I mean, it is obvious for the experts, and I think it's perplexing to the non-expert, but the systems with large electron correlation contributions, systems involving bond formation and cleavage, excited states and transition states, they are the target states. For molecules, well, strong correlated systems. And for chemical reactions, so this relationship between the reactant and product. For materials, there is the generalized density function method that's often used. When you don't have sufficient accuracy with that, this could be used. And surface and interface. So that's where physical properties of both are reflected, and that would be a target of computation of this method. So in concrete terms, with what kind of companies we have worked with? 3 companies we have listed here today. Nippon Steel for iron crystals, and with Total Energies, metal organic framework computation, and with Roche pharmaceutical company for protein ligand interactions. So I'd like to talk about these 3 cases. So with Nippon Steel, we conducted energy calculation using quantum algorithm. So steel is used everywhere. It's all around us. And so it's a very valuable material for industry. So to calculate the physical properties of this accurately will be very helpful. It may expand new possibilities of this material. Now, so there you usually use DFT for calculations for iron crystals for periodic structures, but we considered whether you can have more accurate calculation with quantum computers. So what is the issue in doing this calculation? As I've been repeating, our unique characteristic is that we can implement the algorithm on NISQ devices. You can actually compute on the NISQ devices. And there is impact of noise, but you want high accuracy. But the noise would lower the accuracy. That's the concern. So in this research, we worked on those issues. And so on actual device, we put the algorithm, and we tried to minimize the impact of noise. And we showed that we can have high accuracy calculation on a NISQ device. Wonderful example here. Next example with Total Energies, result of R&D with them. This is for metal complexes, and we wanted a high accuracy calculation for adsorption. So metal complexes can absorb gases like H2 and CO2 at their metal centers. They have such unique characteristics, so there's an expectation for them to become new environmental materials. Now, of course, it's very difficult to calculate because it has metal centers. And with the NISQ device, with small number of qubits, how can you calculate this is the issue. So with a large molecule, how to do the calculation was the issue that we worked on. And we have this fragmentation method, which is unique. So you break them up, and you can calculate the target energy. With this computation, with that kind of methodology, you can have a framework to calculate this kind of large structures even on the current NISQ devices. Lastly, example with Roche. As you may be well aware, in drug discovery, computational chemistry would be very effective if you can use that to find new drugs or develop new drugs. And so there is this protein ligand reaction that's quite important in organisms. So how can you calculate that is what we worked on here. And similar to the metal complex example, molecule is large, so we apply the fragmentation strategy to break them up. But the proteins has a large number of molecules, so it's difficult to handle that. But we look at the ligand, and we did the fragmentation and calculated the energy of the binding energy. So similar to the total energy example, we use the fragmentation method, and also we put it on the actual device and calculated. And for multiple compounds, we did the computation, and we were able to plot this and evaluate quantitatively. So that was the achievement of this. And sorry to repeat this, but we're doing this on the NISC device. We're implementing the algorithm on this NISC device. We're very strong with that. And so I'd like to talk about the importance of error correction with NISC device. Left-hand side is with no error mitigation. And right-hand side is with, and you have the numbers on the horizontal axis, types of compounds, and you have the delta E on the vertical axis. So how far is it from the noiseless calculation? And closer to 0, if the distribution is smaller and closer to 0, the better the result. So you can see without error mitigation, it's quite dispersed, quite far from 0. But with the error mitigation method that we developed, you can see 2 orders of magnitude better result, much closer to 0, much less dispersion. So by using this kind of technology, the energy for protein ligand connection, you're able to do the calculation for the binding energy, and you're able to get the result with quantum computing. So this is the summary, and I think you're well aware of this. The field of quantum computing on a global basis, various companies are entering and starting to do R&D in this field. And we explained the quantum chemistry computation example this time. So quantum chemistry in action, a global perspective, is the title of this talk. And to summarize, in the field of quantum computational chemistry, it's important to conduct R&D from both quantum algorithm and hardware aspects to achieve quantum superiority. In Quanto, supports R&D of quantum algorithm using quantum hardware in the NISC era. And people in industry like yourselves, in the near future, you can aim for a quantum advantage, and you can focus on the target area of post-Hartree Fock calculations. So lastly, a little bit of advertisement. New quantum chemistry calculations with quantum computers. So 2 business models that we have. First, using in quanto technology, well, we can provide our experts, our researchers, and for your use cases, we can have discussions. So we can support your development. So R&D collaboration is one service we can offer. And 2 months ago, in Quanto has been launched as a platform. So this is also offered as a subscription service. So you can use the InQuanto platform on a subscription basis, and so it can be used in your development platform. So you can do the cutting-edge quantum computing research on it. So let's start quantum computing with InQuanto. So let's, if you want to do quantum chemistry computation, please consider using InQuanto. Thank you very much.
平岩さん、ありがとう。